want to talk a little bit about permanent magnets, because we've been introduced to the fact now that a current carrying wire creates a magnetic field around it, fills the space around it with a magnetic field. And so let's talk a little bit about permanent magnets. And the idea, our models aren't always correct, but they help us oftentimes to visualize a phenomenon and maybe picture or imagine how it might take place, even if we know it's wrong. So an example would be that, that electrons orbit the nucleus of the atom like tiny planets orbiting a sun. And we know that that's not the case, that it's much more complicated than that, that the electrons are not really in any one place at one time. It's a cloud of electrons around the nucleus, and it's not as simple as point objects orbiting the nucleus. But if you wanted a ballpark estimate for the force on an electron as it's moving around in the nucleus, then you could maybe use that model that it's a point object orbiting like a planet orbiting the nucleus, and you'd probably come up with a ballpark. We know it would be wrong. The calculation wouldn't give us the exact value, but maybe it would get you in the ballpark. Maybe it'd be within an order of magnitude, something like that, which is better than a wild guess, right? And it gives you something to imagine because we can't visualize electrons, but if you have this model, maybe it helps you visualize. So our model for permanent magnets is that magnetism is a manifestation of a moving charge. And you can picture that if you have actual charges moving in a wire, or even just moving by themselves, a moving charge creates a magnetic field around it. A moving charge in a wire, that's a current, creates a magnetic field around the wire. But what happens at the atomic level? Some atoms, actually the atom itself acts like a little tiny magnet. And an iron atom is one. An iron atom acts like a little magnet. And the reason is, or our model is, that there's electron motion that contributes to that. Two ways. One is that our electrons, the electron cloud, the motion of the electrons in the electron cloud typically is all random and cancels, the magnetic effects cancel each other out. But sometimes it's not quite completely random, and you have a net magnetic moment from that orbital motion of the electron cloud. And then the other one is that each electron acts like a tiny magnet. And when the electrons pair up in the atom, they pair up with opposite magnetic moments. So they tend to cancel each other out. But if you have an odd number of electrons, then you can have some net magnetic moment due to the magnetism of an electron. Okay? So due to the electrons in the iron atom acts like a little magnet. And when iron forms, the magnetic moments tend to align themselves within small regions of the iron. We call those domains. So in a chunk of iron, as it's forming and cooling, you get these domains where the iron atoms, all the iron atoms in this domain align themselves with their magnetic moments pointing this way. So that domain acts like a permanent magnet with the north end pointing up where that tip of the arrow is. But for some reason in the domain next to it, they aligned slightly differently. Maybe they aligned in this direction. And over here, maybe they align this way and that way. And so the domains tend to be random. And this chunk of iron does not act like a magnet because these domains are all random. The effects tend to cancel each other out. You pick up a paper clip, it doesn't pick up another paper clip. It's made of iron because the domains are all random. It doesn't act like a permanent magnet. But if we take this and we put it into an external magnetic field, or we held up a magnet next to it, let's hold up a big magnet next to it. And here's our chunk of iron with its domains. Something like that, right? Now what happens, those domains, like little compass needles, want to align themselves with this external field. Maybe I'll draw them in a different color. It's getting kind of, how about? So the domains try to align themselves, maybe not perfectly, but for the most part, they align themselves with this external field, at least they try to, as much as they can. Now, this chunk of iron, which had no net magnetic moment before, right? Those were all randomized. It didn't act like a magnet. Now, because the domains have aligned with this external field, this acts like a magnet with the north end over here and the south end over there. So what happens to this paper clip or this piece of iron when we hold up a big magnet next to it? It's attracted, right? We can pick up a paper clip with a magnet.